Welcome to the guide on producing the sodium chloride or NaCl crystal. In this video, I will walk you through the entire process of harvesting NaCl crystal and then talk about the fascinating physics behind solid state physics. Let's go. First, we need clean containers, table salt, or for fancy people, NaCl, filter water, and a spoon. For strict, rigorous experimentalists, you can buy an industrial grade NaCl, but for budget physicists, table salt will do if you are lucky enough. I bought both because the assignment is graded. With these materials prepared, we can start making the supersaturated NaCl solution. Set up a heating device and add in filter water. Theoretically, we know that we can follow the solubility guideline of NaCl, which is 40 grams of salt per 100 milliliters of water at 80 degrees Celsius. You can measure ingredients accordingly, or simply just add a bunch of NaCl until they no longer dissolve in the water. Stir regularly for a homogeneous mixture. When you see small white flakes forming on the surface, it's time to remove the solution from heat. These flakes indicate that the solution has reached its saturation point and the surface solution has started to crystallize. Allow the solution to cool and stabilize in a covered container for about 12 hours. Covering prevents dust and impurities from contaminating the process. After 12 hours, you would observe some deposit at the bottom of the container. Carefully transfer the clear solution on top into another container, leaving any undissolved deposit behind. Cover this container with tissue paper and let it sit undisturbed for 3 days. You should see sunlight deposit on the first day, and on the second day, cube shape starts to form. Of course, the exact duration taken will vary depending on environmental conditions like temperature and humidity. And finally, after a week, this is the result. Now let's talk about the physics. Crystallization is based on the principles of solubility. The NaCl solubility increases with temperature, and if enough NaCl is added, the amount of dissolved NaCl will reach the blue line, which is the saturation equilibrium for a given temperature. Any excess NaCl will not dissolve, and the solution is said to be saturated. But when the solution is allowed to cool, temperature decreases and the solution moves into the supersaturated region, meaning that there is more NaCl than the solvent can dissolve. NaCl starts to nucleate and grow in order to deplete the supersaturation at constant temperature until the solubility equilibrium is reached again. Evidently, NaCl crystal has a sharp defined cubic shape. We know theoretically that NaCl is a face-centered cubic lattice crystal with the arrangement of sodium ions and chloride ions alternating in a repeating 3D pattern. Each ion is surrounded by six oppositely charged neighbors in a symmetric coordination, making it electrostatically stable. This symmetry naturally extends to the macroscopic crystal, giving it a cubic shape. The shape reflects the internal order and symmetry of the lattice. The well-formed flat faces occur because planes of relatively lower Mahler index are more stable than the others due to lower surface energy. As the crystal grows, new atoms attach easily to the rougher and less stable parts of the surface, but less easily to the flat stable surface. Therefore, the flat surface tends to grow larger and smoother until the whole crystal surface consists of these plane surfaces. But in practical, perfect cubic NaCl don't always appear. Instead, some looks like a few cubic structure merged together, and some is missing a corner. This is due to the presence of impurities from the NaCl solid, water, dust in the environment, attaching to the crystal and disrupting its structure, which is the reason why we use industry-grade NaCl, filter water, and covering the containers, but out of the laboratory, the environmental factors are hard to avoid. The rate of crystallization is another factor. If the crystal grows slowly, the impurities may attach briefly to the growing crystal lattice, but they soon leave as the compound with a more suitable geometry comes in to take their place. Suitable cubics stay more readily in the growing lattice. If the crystal grows too quickly, the impurities can be trapped inside the crystal being formed before being displaced. In my practice, I use tissue paper to cover the container so that the NaCl solution is not directly exposed to moving airflow, but allowing moisture to diffuse through, controlling the rate of crystallization. That's all you need to know on how to DIY NaCl crystal at home. like and rewatch, please. Thank you.